So thank you. I want to thank Krishna for inviting me to give this presentation. I'm super excited. I've kept track of the geoenvironmental engineering seminars that Krishna started during COVID, and they're an amazing series. And I'd like to add my contribution today with elevated temperature landfills and discuss some of our prior field observations and how that has come to our numerical modeling more recently. And I'd like to acknowledge my co-presenter, Alborz Benenajad, who on the back end of the presentation did numerical modeling was his work. What are typical MSW temperatures? And what I mean by MSW temperatures, specifically referring to the waste temperatures, because a lot of times we think about the gas wellhead temperatures, and that's what the NSPS regulates, and that has to be less than 131 degrees Fahrenheit or 55 degrees C. So an example of typical temperatures in a landfill is here in this figure. We have depth on the y-axis, we have temperatures on the x-axis. What's interesting here is the gas wellhead temperature, which is this blue line, and it's a long line representing where the screen wells are, the slotted gas well pipes located, and that's on average about 45 to 46 degrees Celsius. So that represents an average based on the radius of coolant filled out gas well, what the temperature is. There is a downhole thermocouple array also located next to that gas well, and that's the red circles here. And you can see there is much lower temperatures near the surface. Obviously, there is a heat sink to the atmosphere because of that. And then once you get beyond that, let's say 10, 12 meters below the top of the landfill, and you get this constant or near constant temperature of about 65 to 70 degrees Celsius. So in fact, much, much higher. In this case, the difference between the gas extraction well and the downhole thermal is about 30 degrees or 20 to 30 degrees Celsius. The green triangles represent samples that were tested with a temperature gun as they were excavated from the landfill. So during boring, they took samples, and for the most part, if you want to get a more representative idea, and if you don't have a downhole thermocouple, they provide some kind of average of what the temperatures are inside the landfill. So what we've seen here are temperatures inside the landfill of 60 to 70 degrees C, which is much higher than what we use for gas wells. So as we kind of shift over, what is a typical MSW temperature? Well, part of that is also related to the biology. Here's a great recent paper by Shoup et al. Coming from Mort Barlaz's lab that looks at what are the limiting temperatures for methane generation. That's key for a healthy landfill. We want that renewable energy methane generation and capturing it. So again, this kind of dovetails with the temperature we're seeing here. It's about 65 to 70 degrees Celsius. It's kind of like an upper limit of maximum MSW temperatures that we see in a landfill. So the figure on the left here shows downhole thermal arrays. Those are DTAs. Each one of those points represents sensors, temperature. And what I've done here is taken the temperatures for all of these data points and stitched them together to show that, similar to what we had in the last slide, temperatures are a little bit cooler at the top and bottom and warmer in the middle, about 60 degrees Celsius. So what is then a typical temperature that we've observed for an ETLF? And on the right shows as an ETLF is coming through these downhole thermal temperature arrays, the temperature increases, especially at DTA1, upwards to 130 degrees Celsius. So 250 to 280 degrees Fahrenheit. That is the temperatures that we've seen for an ETLF. And so now we have some kind of sense of judgment on typical landfill temperatures and the temperatures that we've observed in an ETLF. So with that motivation, I've set up the presentation in three parts. Part one is looking at the field observations, what I call the progression of indicators of an ETLF. Part 2 takes those field observations and kind of like a jigsaw puzzle, pieces it together in terms of what's happening spatially and temporally. And then part 3 is going to be looking at the next step beyond the spatial classifications, is doing some modeling of what an ETLF might look like. And this is just the initial steps for that. So in terms of the progression of indicators, we're going to use a case study in Ohio. On the top left is an aerial imagery from Google Earth from 2000. The cells of interest are going to be right here. I'm going to put my laser pointer so you can see it. Cells 4 through 6, they were constructed in the early 2000s. By 2006, you can see that these cells are pretty much complete. They've been filled up. When we get to about 2009, there are reports of elevated temps and carbon monoxide in 5 gas wells. And that, if you look at the Google Earth maps, you'll start seeing a geomembrane located on the cell 5 of the facility and here at the corner. And those 5 gas wells correspond to this specific location. By October 2009, there's cracks and toe bulging in this general area, so some kind of slope movement. And as we fast forward, 2010 and 2011, they start seeing significant settlements on the order of 4 meters. And as we keep progressing with the Google Earth imagery, we start seeing kind of a bowl forming in the center that's exhibiting the extreme settlement. And this is a photo that I took circa 2014 or 2015, and I was located here on the highway looking at this specific cross section here. So in one regard, we're looking at the normal landfill here, which is pretty much right here. So not disturbed, that's what the elevation on the landfill is. And then as you translate from unimpacted to impacted, you can see the stark contrast in elevation on landfill, showing that the ETLF has been ongoing for quite a while. So that was the settlement starting in March 2010 or prior to 2010. And then, of course, with all of these ETLFs, because you have such high settlements, gas production, you have a lot of complaints, and they were being amplified or accelerating with time from 2009 to 2011. So what made this case study quite unique is the instrumentation and the monitoring program. So you have the gas extraction wells, which are kind of a instrumentation or a sensor node. They measure the gas wellhead temperatures, flow rates, and vacuums like we typically do. But they also took samples to take to the lab and measure methane, nitrogen, oxygen, hydrogen, carbon dioxide, and carbon monoxide, which are the 6 key gases that we typically associated with an ETLF. On top of what we were measuring from the gas extraction wells, they had these stability pins. So these are lat-long locations where they're keeping track of their elevation. And so you can use those pins and how they move both northing or easting or lat-long in their elevations to get an idea of settlement and their lateral movements. They did install downhole temperature arrays in cell 4, but the ETLF never made it to cell 4, and I think that's because it's a shallower layer than the other layers. But so it didn't reach it, so the temperatures were quite normal there. So one of the first things that we see from the gas extraction well is changes in temperature correlated to changes in gas composition. As an example, this is one well that gives an idea of the general behavior from many of the wells from the site. Wellhead temperatures well below the 55 degrees C from NSPS, and the ratio of methane to carbon dioxide, which is about 1, which signifies methane and carbon dioxide being produced equally. And so everything is well. And then somewhere around time 500 to 550, we see a gradual increase in wellhead temperature, and with that precipitous drop in methane to carbon dioxide ratio. So that's that interplay between increasing temperatures inside the landfill, although albeit this is a wellhead temperature, but the gas providing another proxy or even a better signal, faster signal that there's something changing inside the landfill. So with those two signals, the temperature and flow rate, the other two signals that we see correspondingly is hydrogen starts to pick up as the methane starts to decrease. One mechanism for that is the landfill reverting back from methanogenesis to acetogenesis phase. There are other potential reactions, the water gas shift balance, that could be one. But acetogenesis is one that kind of makes sense with being acid locked when the temperatures increase. We also see as the hydrogen increases, carbon monoxide increase from about 0 to almost 2,000 parts per million. And that's reflected in a good indicator signal of smoldering combustion. Another signal for an ETLF is leachate, and specifically the production and migration. A lot of landfills don't do specific recording of how much leachate they're pumping from specific sumps. They kind of keep a track through maybe pump operations, and that's the case for this facility. These dots here represent where the sumps are located for each cell. So cell 4, 5, 6, 7, they're all color coordinated here on the graph on the right. The elevations that you're seeing here are the bottom contours where the liner and the drainage systems are located. So what we're going to use is the cumulative hours of operation for the pumps. And what we'll look at is the orange dot first, and we'll see that they really didn't use it too much at cell 4, and they really didn't use it too much at cell 6, which is the green. So those are comparatively less used. And that will make a lot of sense when we show some of the next slides. A lot of the action was happening in cell 5 and 7, and we can see that the operation of those cells were significantly greater than the other two cells. So that gives me, that gives us a sense that perhaps the leachate production is increasing. Think about those high temperatures driving moisture to different parts of the landfill. And as a result, they needed to be collected and removed. Another observation is the leachate that does come out from the facility is going to be black, and that could be a combination of plastics, charred materials, the leachate, which is typically kind of an amber brown, changing colors. Another indicator is elevated gas generation and pressures. One way of visualizing this is through a video. And this is another facility, not this facility that I'm using as a case study, but just to demonstrate. They're drilling here for a new gas well, and as they're opening up the seal, you can see kind of an artesian pressure, just like a geyser, like Old Faithful, as gas is released from the landfill. So artesian pressures of 20 feet or so, not uncommon here in this video. So let's go back and look at some observations from gas wells. What are the positive pressures that we report? Remember, during gas well operation, we're typically applying a vacuum. So these positive reactions are actually overcoming the vacuum and showing a positive presence. So in extreme cases of biodegradation, maybe you have wells that are watered in or along those lines, and they have a slight positive pressure if the vacuum's not working. So that's about 0.5 to 3 kPa. Now, other facilities that we've monitored with aluminum reactions, so those are the aluminum dross, aluminum production waste reaction, those have increased quite a bit. Those are about 45 kilopascals as a maximum. Areas where there's ETLFs, when we're thinking about processes such as smoldering and pyrolysis, those have been up all the way to 75 kilopascals. And so another way of thinking about where is this gas pressure coming from? Well, I think there could be two mechanisms. One of them is using the ideal gas law. The idea here is if your temperature is increasing, remember I said we're going from 50 degrees C to about 120 degrees C. So if we're assuming that the landfill is a constant volume, which to some degree with an ETLF, they put a geomembrane over it and they're trying to seal it very well, that's a really good assumption. And if you make the case that the internal landfill temperature, gas pressure is about atmospheric, 100 kPa, well then the temperature increase is going to correspond to about 23 kilopascal of increase in just pressure. So that's about 2.3 meters of water headers. And you can kind of put those numbers in perspective here that just the change in temperature could be contributing to these increases in gas pressures. Another mechanism is gas generation. We know that for the most part, the biodegradation of MSW anaerobically through methanogenesis is going to create from the literature about 140 cubic meters per metric ton of waste. This is a slow process. I think we've all seen the studies that show, whether it's land gym or else other facilities, that this is a decadal process, years, half a decade to decadal process to achieve this 140 cubic meters. On the other hand, if you look at processes such as smoldering, combustion, pyrolysis, all of us have cooked, grilled outside. We know that smoldering pyrolysis is a much quicker process. And if you look at the literature, it produces about 350 cubic meters to about 350 cubic meters per metric ton. So not only is that over 2.5 times greater than just MSW decomposition, but this is a much faster process. So I think of it as 1/3 kind of ideal gas law thermodynamics, the other 2/3 of we're producing a lot of gas because we are thermally breaking down the waste. Just like you would see with gas pressures, there's a lot of leachate outbreaks and pressures. This is quite common, and you would see leachate geysers as well. So moving then to the slope movements from the surface pens. Each one of these arrows that you see in this diagram represents the surface pen. And so what we're doing here in this graph is we are tracking its lateral movement with time. And so on the x-axis here, you can see the dates are changing. So what we see with the arrows initially is initial movements are here in cell 5, but over time, we don't see anything in cell 6, but we see the ETLF really moving towards cell 7. These arrows that you see are the direction of movement, but they also are an indicator of how much movement. The legend here to the top right shows that this size arrow, which is 2 centimeters in the paper itself, or if you look at the diagram size, is equal to about 10 meters. So there are some locations here that have moved over 10 meters from their original location. So it really gives a perspective of how much pressure or force, just like a Newmark sliding block analysis with an earthquake, how much pressure can be pushing this landfill out when you have an ETLF. So starts in cell 5 and migrates towards cell 7 over the course of, I'd say, from early 2012 through end of 2013, so almost a 2-year period. Of course, surface manifestations are going to be tension cracks, and these are going to be different from differential settlement cracks because these, when you look at the cracks, they're going to just be split next to each other. They're not going to have an offset. So that's good, an indicator that these surface pins, what they're showing, are actually being confirmed with what we're seeing on the ground. I mentioned differential settlement. The photo on the top here you've seen before, and I'm showing from the red line kind of where the landfill used to be and how much it's dropped. Of course, a safety hazard is if the ETLF, through some migration, facilitates a sinkhole to develop, and those have been found at this facility as well. But let's put some numbers to that settlement. We have a couple of data points here. One of them is the green triangles, and that's what I call normal or anaerobic decomposition. And that's about 1.5 feet per year. That comes from cell 4. Then we have another pin that comes from the ETLF area, and we see that the settlement rates are varying over 3 different periods. So the initial period where we think that ETLF is coming towards that pin, I call it the kind of the heating front, kind of preamble. It's about 6 feet per year. So already 3 to 4 times higher than what we'd see from from normally at that facility. And then I think around day 500, the ETLF really starts to take its hold, and the slope, even though it's only for about a year or so, it's very steep. We're losing about 10 to 40 feet, 30 feet of landfill height in just over a year. And so if you equate that, if you look at the actual numbers, it's about 50 feet per year. Afterwards, it starts slowing down again. I think this is kind of the afterburners of, or after the smoldering has, or ETLF has moved through kind of its self-compacting and what's kind of the heat residuals in the facility. So you have about 9 feet per year. I want to put that in perspective as well. There are very nice studies as well that look at bioreactors and the accelerated settlement that we see from them. And so here's a classic paper from Craig Benson in 2007, where they look at bioreactor settlements, and they have on the order of 5 to 11 feet per year. So that puts it in perspective that normal bioreactor obviously is accelerated, but smoldering is on a whole different magnitude. So what I've done in the next slide here is I took the normal settlement curve, which is now a blue diamond, and also the smoldering settlement, which is still here, the red circles. And I've incorporated the gas well right next to this stability pin, and looking at when does the settlement occur, when does the gas changes occur. And this is very common. We see that the ratio of methane to carbon dioxide is around unity. And around day 600, it kind of transforms to almost less than 0.2. But the settlement, nothing has happened until about day 800. So there is a time lag from when gas changes at the gas well and when actually that what I call the heat core from the ETLF moves through and starts pyrolyzing or thermally breaking down the waste. So if we start then putting together the changes of elevation and slope movement, we see in this figure here, we can start kind of piecing together which one comes first and what's their interplay. We're going to pick up the story here in August 2010. And when the data is already present, there's already quite a bit of settlement. So the contours here represent about 4 meters or so in the center in cell 5. And you can already see that there's a lot of toe movements, or there's some toe movements here for cell 5. So we're going to play the video. And as we progress through 2010, we can see that the settlement bowl is increasing. Then the arrows surrounding the settlement bowl are also increasing. And as it expands out towards cell 7, we start seeing those arrows pick up as well. And this is a really good demonstration that settlement bowl where we're seeing the settlement, that's where a lot of the heat core is happening. But in front of it is pushing the heat, the moisture, changes in gas, and potentially slope movements in advance of that. So there is a time lag as well there, that the slope movements are happening before the vertical settlements. So when we look at all the different things we've just gone through, from gas wellhead data to stability pins and just the observation from the site itself, we've kind of developed this progression. So elevated gas and waste temperatures. You have to have those elevated temperatures to then change gas composition, which concomitantly is going to increase the gas pressure and flow. With the gas increasing, the pressures increasing, you're going to have outbreaks and increased volume. That is going to then facilitate the movement or lateral movements of your slopes, could lead to potential instability. And of course, we're going to see excessive settlement. So the next, as we go from the progression of indicators, let's look at how the landfill is changing spatially. So the figure here shows specifically the red dots show gas extraction wells. And when we started looking at the data, the area in orange patch is areas that those are the gas wells that have already been impacted by the ETLF. So they're showing 0.2 for the methane to carbon dioxide ratio. They're showing potentially high gas well temperatures. The areas in the green hatch are cell 4, and they were not impacted at all, and those are kind of a baseline. There are a number of different gas extraction wells that had stability pins located right next to them, and that's what's highlighted here in purple and green. And we're going to use those as some indicators of what's happening later on. So let's look at spatially how the gas wellhead temperature is changing. Well, at the very beginning, we see that just like we saw for the slope movement and settlement, here at the bottom of cell 5 is where we're seeing our initial hotspots of gas well temperatures of 80 degrees C. So in a sense, it's provided us a good indicator where the ETLF is. The numbers that you see associated with these gas extraction wells is the oxygen content in those gas wells for that specific month. So there is some high gas or oxygen concentrations associated here. As we move forward to March 2010, we still see that the gas wells are quite high, but we also see a lot of blue points here. And I think that is something that's a problem with gas wells and using them as specifically the only signal for an ETLF is if you do get air intrusion, maybe there's a seal broken with the gas well that lets air just directly into the well. You're going to see these cool spots that are more than likely not going to be actually reflecting the waste temperatures. And that holds true as you go from September 2010 to even more extreme March 2011, where the oxygen concentrations are quite high. So we're probably seeing that the gas well itself, from an engineering performance perspective, there's potentially seals broken and air is just getting inside the well, just being short-circuited. What has been a better signal spatially is doing some geostatistics with the methane to carbon dioxide ratio. So when you stitch those together using semi-variograms, they actually come out quite beautiful. And you can color code them. So the red here represents no methanogenesis. That's pretty much 0.4 or so below. Then you have kind of, when I think of a stoplight, you have the yellow or orange from about 0.6 to 1. That's the transition that it's going down. And then anything above 1 is healthy, or we have the green light. So you pick up in January 2010, you see that a good portion of cell 5 and cell 6 have limited methane generation. And then we see how the yellow then starts to spatially migrate through the facility from cell 5 and 6 into cell 7, and it progresses all the way through cell 5 and kind of stops here at June 2011, the last month here. So then if we take a look at strain rates, we want to use that also as a signal of how the settlement bowl is moving. And I took one stability pin here, surface pin, and one here to kind of just show what's the strain rates. So we've seen the magnitude versus time, kind of like a settlement curve in the previous slides. But what is the strain rates? Well, if you normalize it to the actual thickness of the landfill at where the stability pin is located, you get about, before any ETLF, normal conditions on the order of about 1% to 2% per year. And that's, I think, quite normal. If you look at the literature on settlement for MSW landfills, I think they're less than 3%. However, as you get towards cell 5, the stability pin in cell 5, we see that it jumps all the way almost to 10% per year. So there's probably some transition zone as it reverts from greater to the 2 to 4 that kind of tells you that, hey, we're transitioning to the ETLF. And if you look at then color-coded spatial maps of strain rates, and I've done again where anything around 2 and lower is green, around 4 is kind of the orange to yellow, and then greater than 6 is direct evidence. You can see it's localized here in cells 5 and 6, just like we've seen before with the gas. And then, interesting enough, as it starts to migrate, it doesn't always stay red for the entire facility like we saw for the gas. In this case, you can see that it's kind of like a front moving through the landfill. That's the arc here that you see in October 2011. By May 2012, it's more or less in the center of cell 5 and cell 6. And then it's kind of by November and then May or 2013, it's moving towards cell 7. And really at that point, it seems to be kind of done its course and settlements have come back to what I call normal levels. Now, it is green here saying normal levels, but I would wager that the gas and methanogenesis is probably not happening here. So it's a really good pinpoint of where those ETLFs are really churning through the waste. So if you actually plotted what I call the middle of the signals, the yellow parts, between the two, you can kind of get an idea of their spatial classification. So when we pick up the story in September 2010, we see that the methane to carbon ratio has got most of cell 5, cell 6, and into a little bit of cell 7. And the settlement, the higher settlements from -2 to -4% strain are just behind there. So they're never going to be caught up with how the gas is changing. And that's been the case from all these data points from October, May, October 2011. You can see that the gas is changing in front of the ETLF itself. And that makes a lot of sense. I think we've seen now that interplay between how gas changes before the settlement. So when we took all this data and put it together with the indicators, we kind of came up with a conceptual diagram of what might be looking inside the landfill. And I say what might be looking because as much as I've shown a little bit of the downhole temperature sensors and their data, a lot of times they fail when that ETLF moves through. It just turns through the thermocouples and we lose track of what's actually happening in the heart of the ETLF. So on the very left is anaerobic decomposition, same old normal operations like cell 4 for the facility. And then what's happening in cell 5 and cell 7, there is a heat core where there's that exothermic reaction from smoldering, and which is then facilitating pyrolysis of the waste. And that driving heat then is what you think is creating another front or an envelope of change in the landfill. So you have normal here, just typical biochemical reaction zone. You have the exothermic chemical reaction zone. In the middle here, that's where I think we're seeing the gas changing and the temperature changing from the gas well. So I've called that the gas front and temperature fronts. So we took all the data that we've compiled for this case study and said, well, how do we tell this zone from this zone? And what we're going to be using is wellhead temperature and the ratio of methane to carbon dioxide. That's an indicator for us to kind of get an idea of the heating front. So the data points that you see here are actually data points from gas wellhead that compiled all those data points. And for the most part, you can see a trend that the wellhead temperatures are about, on average, 50 degrees C. Sometimes it's a little bit higher, reaching up to 60 degrees C. But we also see a lot of productive gas oils here. The methane to carbon dioxide ratio is well above 1. They're kind of at that 0.8, almost transition point. At around 0.5, we do see a distinct trend that as the wellhead temperature is increasing, the methane to carbon dioxide ratio is also decreasing. And so that's when we start seeing that trend. And I think this is the most important aspect, is the trend of wellhead temperature versus gas changing. That's symbolic of the heating front. For the smoldering front, we're using methane and carbon monoxide as indicators. Carbon monoxide is an indicator of smoldering combustion. So when we start seeing normal decomposition, 50 to 50% per volume methane, and the trend starts to decreasing. And as that happens, you start seeing increases in carbon monoxide. Well, that's kind of giving us an indicator that the landfill is more than likely inside that heat core. Now, obviously, you can use settlement rates as well if you have that data. So moving to the last part of the presentation, I want to go through this. And the reason why we're going to switch gears here to do some modeling. We've talked a lot about what's happening from field observations. But one of the big questions for the industry has always been, well, how does this start? And so obviously you need to bridge the temperatures of 55, 60 degrees Celsius with the temperatures that can get you up to where smoldering could happen. There have been a number of exothermic or reactive waste that as researchers we've looked at. So specifically aluminum production waste, that's a metallic aluminum. That is quite exothermic. You have calcium, so you have a lot of ash, coal combustion residuals that have calcium oxide. You can also have calcium oxide, the hydration of it, and then the carbonation of it afterwards. And we've seen landfill temperatures of about 170 degrees Fahrenheit, 200 degrees Fahrenheit for aluminum. But what's really missing here is these are enthalpies, joules per gram of whatever's being reacted. But what we need to do is convert this delta H into what I call power, watts per meter cubed, that the energy use, joules per second. That's going to really help us or tell us that transition from anaerobic biodegradation to potentially these higher order heat generation processes. So we know that there's been a lot of investigation of chemical reactions in landfills. And so what we wanted to do in our modeling is look at aerobic reactions, because one thing that you do need for smoldering is a little bit of oxygen. So aerobic reactions provide some form of heat, and we would want to quantify that. And then also there's presence of oxygen, which could facilitate the subsequent reactions. We also know that aerobic reactions are about 10 times more exothermic than aerobic decomposition. So we know that this is a higher order type of reaction where it's going to be more exothermic. There's also been limited numerical investigations in aerobic reactions. When I think of aerobic reactions in landfills, I think of some seminal work in the early 90s looking at air intrusion through the cover system due to changes in atmospheric pressure from cold fronts and so forth. Then I also think of work in the mid 90s, early 2000s that looked at aerobic decomposition as a sustainable way of landfilling. The latter one was really focused on pushing a lot of oxygen into the landfill. So it's not really a good proxy for what might be happening in a landfill, because in a typical MSW landfill, we just have a local zone of aerobic reactions. So we wanted to model aerobic reactions, but localized, and understand their spatial, temporal, temperature and pressure evolution. And also we're going to use two different scenarios. We're going to use air intrusion through the cover. So that's the one that we always think about, but also one that when we talk to the industry is airline brakes as possible mechanisms to reduce oxygen and aerobic reactions. So what do we want to quantify? Well, how quickly does temperature increase? How long does it stay elevated? But more importantly, what is that heat generation rate? What is that number that then can help us down the line? To do this modeling, we're going to use the TUF2 framework from Lawrence Berkeley National Lab. And specifically, we're going to use the landfill bioreactor model. So this is a 2D model that does simulate MSW biodegradation along with the flow and transport of gas. So what I call the multi-phase, multi-physics of the landfill. So Kurt Oldenburg developed T2LBM in the early 2000s. In terms of, I won't go through much of the background of the actual program, but what it does for the biodegradation is it doesn't model all stages of MSW decomposition. It specifically starts at the methane formation, and it uses the acetic acid as kind of a proxy to get to methane generation. So the way T2LBM and TUF works is it has an inert solid, and a lot of the actions happening between gas and liquid. And the gas and liquids are going between phases using Henry's law. So in this model, a simplifying assumption is we're not actually decomposing the solid material. What's happening is we're using acetic acid in the liquid to facilitate gas generation. And so then the liquid and gas volumes are changing from there. Here's an example. Here is the cross section of the facility we use, or the landfill we use. It's not a match to the case study that I showed earlier. This is more kind of a conceptual landfill based on a real landfill just to kind of do demonstration, realistic demonstrations of aerobic reactions. So we have 3 different layers associated with this landfill. We have a shallow layer, intermediate, deep. The properties of these different MSW layers are going to change. Think of shallow as kind of sand-like, so more permeable, and then deep, more clay-like, less permeable. We have 6 different gas wells incorporated here. The reds represent the slotted or the screens for those gas wells and where it could potentially be producing or collecting gas. Obviously, because the shallow layer is more permeable, a lot more of the gas is going to be collected in the top layer than the middle layer than the deep layer. We've had to make some simplifications for this modeling, so I think there's always a good discussion of 2D versus 3D. I think 3D would be more representative of a landfill, and that's because we have gas wells. Gas wells, when you model it in 2D, imagine this is a plane strain problem, so those gas wells are going into the page for infinity, which is not true, right? Those gas wells have a radius and influence associated with it. So that is one simplification that we've had to make here. And obviously, down the line, it would be good to build a 3D model so we can see the interplay of gas wells and the reactions themselves. The other one is instantaneous versus stage construction, meaning that landfills are built in stages. This specific facility that we used as a kind of a starting point was built very quickly or rapidly, such that we could make an argument that because it was built so quickly, the landfill wasn't really seeing stage construction where different parts of the landfill are seeing different parts of decomposition. We applied a atmospheric boundary condition to the top, and then we have clay layers that are impervious at the top and bottom. So essentially pretty much a sealed landfill. And we then used for the biological properties for the shallow, intermediate, deep, we use the same, what I call, like if you have land gem, you have this one curve that shows gas production versus time. We use the same curve, we just started them at different points of that curve. So shallow is very early in that curve, intermediate's in the middle, and deep is on the back end of like a land gem model. Here are the material properties that we used. I think what would make sense is you go from shallow to deep, the densities and porosities are changing, the verticologic conductivities are getting lower, and the heat conductivities are also increasing as you get deeper. We did play around with specific heat in terms of the sensitivity analysis, and we'll get to that here in a little bit. We also modeled these materials as partially saturated. We needed to do that to develop an equilibrium at the start of modeling, kind of like a balance, water balance, before we started any kind of biological reactions. And so we used the literature as guidance. Also, as I mentioned, the shallow, intermediate, deep reflect kind of a sand, silt, clay, soil. So there's very little matrix suction that could be being produced in the landfill, just because we're at very low suctions typically in a landfill. So here's what the degree of saturation looks in the landfill. Our idea was to replicate to most that it's a little bit drier in the shallow, a little bit wetter in the intermediate, and it's going to be more wet in the deeper layer. Obviously, if you were to model a landfill, not only would you have MSW layers, but you would also have interbedded covers or fine grain or low permeability layers throughout the landfill. You would have water coming in from precipitation, and those are some of our next steps down the line, but we just wanted to establish this capillary equilibrium. We did model the gas wells. There's a lot of different ways in T2LVM that you can do this. One way of doing it is using the productivity index, and that is a function of a couple of things. One of them is what's the pressure nearby the well. So you can set that pressure. So if it's higher than this well bore pressure, it's going to start collecting gas. It's also a function of skin friction, which we assume to be 0 because we don't have much information about it. And at the end of the day, we took a look at the 2D radius of influence from these gas wells, and we kind of worked with the productivity index to match when we talked to the industry, what is a typical radius of influence for gas wells? And they said on the order of 25 meters, so about 75, 50 to 100 feet or so. And we try to set the flow rate and productivity index to kind of match that radius of influence. So what we see from the gas wells 1 and 6 are at the very edge or ends of the model, and we see they produce the least amount of gas, which makes sense. They're mostly screened in the lower deep layer. We see a little bit more gas being collected in 2 and 5, which is the next sets coming in. And then gas wells 1 and 3 and 4, which are in the center and have slotted wells in the shallow layer, are producing the most gas. So we took a look at how much gas is being produced. And again, we're working with a 2D model, but we understand that this is a 3D problem. What we did is to make sure that the amount of gas being produced made sense. We use LandGem and the basic inputs for LandGem to kind of get an idea of if you had this much tonnage of MSW, which matched between the two different models, how much gas would you get? And so we try to tune the model to achieve that. So here's an example of time history of temperature just for anaerobic decomposition. And this is pretty well established that as those reactions ramp up over the course of years on end, in the center of the landfill, you get higher temperatures and then the edges. When you look at gas pressures, we see at the very beginning and end, there's a blue color, so very low gas pressures because there's a lot less gas being produced. And then during the middle years, year 5 and 15, where there's a lot of gas being produced, or you're in that peak period, it increases about 20 kilopascals. This is an area where I think we could do better in terms of measurements and of understanding what are gas pressures in landfills. We think these are reasonable, but they haven't been validated with actually field observations. We'll also notice for the gas pressures, they're slightly higher in the deep layer, and that also makes sense, lower permeability, higher fluid pressures. The vectors on these plots show where the gas is being produced and where it's moving. So you can see why the center 2 gas wells are collecting the most gases. It's a lot of the gas is coming from this less permeable layer where there is more biogas to be produced. That all makes sense. So we started to then incorporate oxygen into the landfill. So the first scenario that we looked at is air intrusion from the surface cover. And so what we see here is if you just open up the cover system and you have the gas wells operating, it does actually bring in oxygen to the landfill just because you have a delta in pressure gradients. Now, it is very localized. You get that 80 degrees C in a very localized region next to the side slope. And after 1 month of opening and a year after repairing, most of those temperatures have pretty much died down to what's normal in the landfill, very localized. On the other hand, an airline break is something quite different. These are, because a lot of wells have started to accumulate leachate and they need to be pumped, that leachate needs to be pumped out in order to facilitate gas collection. They have pneumatic pumps in wells to remove the leachate. And so those pneumatic pumps then need air for them to work. And so for all of these gas wells, there's air lines going to them. And there are points where the landfill is growing and they put the next 20-foot lift, they raise the gas well riser pipes, but the air lines to those pumps are actually buried inside the landfill, and they can be buried. What we have here is about 20 feet or 30 feet, and those lines then just come up with the gas well. So we use an example where there's an interface between the shallow to intermediate, and there's an airline break, and we want to see what happens. So if I play this video, we have an airline break. You can see a kind of a concave shape form with the oxygen just pouring into the landfill, basically causing aerobic reactions to the maximum that biological reaction can occur, 80 degrees C. We're saying it's repaired after just a week. It can keep going for much longer. And then just over the course of time, that temperature is going to slowly subside, so that I think after a couple months to a year, it's still quite elevated. You'll notice that the shape is concave, so a lot of this action is happening in the shallow layer, and that's because the delta in hydraulic conductivity between the two layers means that a lot of the gas, instead of wanting to go down and create kind of a circular envelope, it's actually just staying in the shallow layer. So when we look at gas compositions, nitrogen versus oxygen, we know that nitrogen's pretty much going for the ride. So it's going to get into the landfill. It's going to stay there until the gas flows take it out. And that's what we're seeing. So you can see how the nitrogen propagates to a good portion of the landfill, and then it's slowly removed over time. On the other hand, the oxygen concentration, we can see that it's very localized, where you get a hot or an elevated area of about 10% where the airline break is, and it decreases as you get farther and farther away. And so by after 1 week, you're about 4 to 8%, pretty far away from the landfill. So there could be wide areas of influence with this airline break. And then all the oxygen has either been consumed or removed after 1 year. And if you look at change in saturation versus temperature, we see that temperature increases to about 80 degrees C in the area where we have the airline break. And we look at the initial saturation in the blue squares, and then we compare that to the green circles. We see that higher temperature is now driving moisture. And so now we're starting to see that interplay of higher temperatures, gas moving, and potentially moisture also moving inside the landfill. I think once we get to modeling the smoldering, combustion, and then the pyrolysis, we're going to see the same behavior, but on a much more amplified. So I mentioned, what is the heat generation for an airline break or air intrusion? And so when we looked at the temperatures at the injection location, and then 10 meters and 30 meters to the left of it, we noticed that it gets up to about 75 degrees C at the injection location. It doesn't reach the full potential of 80 C, which is the upper limit for aerobic decomposition. And I think that's because the cool air is mixing with the heat being produced nearby. Now, as you get farther away from the injection location, that cool air is no longer there, and you're going to reach 80 degrees C quite quickly over a day. And then 30 meters to the left, you still get to the 80 degrees C, but it just takes about 5 days for that air to really propagate to 30 meters away. If we look at the heat flux, now what we're interested in, watts per meter cubed, it's about 400 at the injection location. It's still about 400 at the 10 meters to the left, and then it reaches about 500 watts per meter cubed in the 30 meters to the left. So this is outside the influence of that cool air. And this happens pretty much over a 2-day period. So from about 4.5 days to 6.5 days. So very high heat generation, but very short time period. And you compare that to some classic work by Jim Hansen and Nasli Yesler in 2008, where they look at heat generation rates for landfills in Michigan, New Mexico, Alaska, and British Columbia. Notice how these watts per meter cubed are 1 to 2, compare that to the 500 here, but they're happening over 1,000 days versus this is just happening in 2 days. So that difference in magnitude and the durations being applied is going to change how the landfill behaves. So then we took a quick sensitivity analysis to look at what happens to the heat flux, but also the zone of influence of where there's that higher or elevated temperatures based on airflow, and we have it both in standard cubic feet per minute and also cubic meters per hour. So we started our sensitivity analysis with 1,000, specific heat of 1,000, and then we're going to increase it to 2,000. And so what we notice is the red circles represent 1,000, the blue circles represent 2,000. So as you're increasing the specific heat capacity, that's the ability of that material to hold more heat. It takes more heat flux to kind of raise the temperature and get to a higher aerobic zone. And then once you get to 3,000, it increases slightly more from the blue, so that your heat flux is generally increasing. So increasing specific heat capacity, increasing heat flux with increasing airflow. And then obviously the aerobic zone area, the ellipsoid that it forms is also increasing as well. And so we think of this kind of potentially as a design chart, perhaps. Imagine you have your airflow here, at the bottom, the landfill operator might know how much airflow that airline is getting, and then they can kind of predict what kind of heat flux and aerobic zone they might be seeing. So let me wrap up very quickly. We went over the progression of indicators and the spatial classification, remembering that temperatures can be much different from the gas wellheads from the waste temperatures. I put here about 30 degrees Fahrenheit. We've seen a little bit more from the actual figure that I showed. We have the progression of indicators. We laid out those 6 from temperatures to the gas, the slope movements, and the leachate and settlement. Then we kind of put our conceptual diagram for the landfill zones, the normal, heating front, smoldering front, and we set up some criteria for them, temperatures and methane to carbon dioxide ratios, and then smoldering fronts, methane and CO. And if you have settlement here, you can also use that as an indicator, but that is also a delayed indicator. It's not going to exactly tell you right at the moment that the landfill is changing its course. For the modeling, what was important here is as we get towards understanding initiation for ETLFs, we need to start quantifying the heat generation rates or fluxes. So aerobic is one that we started off with, and the flux is about 50 to 500 watts per meter cubed, and it's a function of how much oxygen is coming into the landfill. And that will get temperatures up to 80 degrees C. So, you know, we see 80 degrees C, but we also see that the heat generation is significantly variable. And I think that's something that we need to trend towards from our waste industry perspective is less temperature, more heat generation. Develop that sense of engineering judgment for that. Now, I do want to note that airline breaks are quite rare, and obviously site operators for landfills are always looking for them, but they do happen, even though they're rare. And so this is one of the first studies to quantify what could be happening inside the landfill. Overflowing gas well through superficial soil cracks. We've always talked about that it introduces oxygen, and it does, and it leads to exothermic reactions, but it's really localized. So we haven't really done an exhaustive sensitivity analysis for the overflowing of gas wells, but I think if you were to compare the two between airline break and soil cracks, airline break is one that is deep inside the landfill and at depth and could be important. But this also shows kind of a benefit. It's not all bad in a sense. That solid waste industry could produce less solid pipe near the top of the waste profile, resulting in improved gas collection efficiency and reduction of greenhouse gas emissions, meaning that you can probably put that slotted height a little bit closer to the surface, not too worried about overflowing in the air intrusion, and get better, richer gas from that. Of course, in any field, with any modeling, you need field validation. I think the field validation that we need is for gas pressures, but also temperatures inside the landfill to confirm. With that, I really appreciate you listening to the presentation. I'm happy to take questions, whether it's myself or Alvors, or send me an email. I really appreciate it. Thank you so much.